Hi there. I'm Jonathan Vandermause. I'm a PhD student in the group of Professor Boris Kaczynski at Harvard. And today I'm going to tell you about some work we've been doing on a unified Bayesian approach to learning many-body potentials. There's been explosive interest in the last decade in using machine learning to train interatomic potentials for molecular dynamics simulations. And you can think of many of these models as falling under two broad classes. The first class, linear models, takes the dot product of a descriptor vector into a vector beta to give you the local energy of atom I. You can think of spectral neighbor analysis potentials and moment tensor potentials as falling under this class. By contrast, there are kernel-based models, which require you to compute a kernel between the environment of interest, di, and all of the training environments, dt. Under this category is GAP, Gaussian approximation potentials, and the GDML models, which stand for gradient domain machine learning. One of the key differences between these two types of approaches is computational efficiency. You can see that in this recent benchmark comparing 5 of the leading approaches to machine learned potentials. Linear models in general tend to come out on top in terms of computational cost. The goal of this presentation is to show you how you can combine the best of both worlds, how you can use principled uncertainties from kernel-based approaches to automate the training procedure, and then take the final trained model, map it onto a much faster linear model, and scale up your simulations to many thousands of atoms. Before I describe how linear models and kernel models can be unified, I'll first show you how we go about describing local atomic environments. Here you can see the local atomic environment of an atom inside of an aspirin molecule. The goal here is to come up with a descriptor vector that is rotationally invariant and also captures many-body correlations in the environment of the atom. We do this in 3 basic steps. The idea, roughly, is to start from a covariant descriptor, which rotates with the coordinates, and to transform that into an invariant descriptor that captures correlations of atoms in the environment. The first step for us in describing the local environment is to choose a basis set, which we choose to be the product of a set of radial basis functions, Rn, and spherical harmonics, Ylm. You can see in the top right that the radial basis functions only depend on the distance from the center of the local environment, whereas the spherical harmonics give you angular dependence. The next step is to compute a covariant descriptor vector C by summing over all of the atoms in the environment of atom I. Drawing your attention to the equation, for each atom in the environment, we look at the interatomic distance vector Rij, which connects the central atom I to environment atom J, and we pass that through our basis set. We do this for each atom, and this gives us our descriptor vector, and notice that we're careful to separate out atoms of different species. This gives us a way of explicitly modeling species dependence in our trained potential. Finally, in order to get the descriptor to be rotationally invariant, we sum over the M index. So we contract the covariant descriptor C with itself, sum over M, and that gives us an invariant 3-body descriptor. This is following the approach taken by Ralph Trautz in this 2019 PRB, but generalized to multiple species. Now that we've defined our descriptor vector, we can use it as input to a machine-learned force field. And I'd like to start with a particular kernel-based approach called Gaussian processes. I've written here the expression for predicting local energies with a Gaussian process force field, and you can see that what's required is performing a sum over all of the training points. And for each training point, you compute a kernel between the test point you're evaluating and the training point. This is the key reason why Gaussian processes and kernel-based approaches more generally are expensive. The cost of evaluating the model grows linearly with the size of the training set. The big virtue of Gaussian process force fields is that you can compute rigorous Bayesian uncertainties on energies, forces, and stresses. Basically, the expression here breaks into 2 components. There's an epistemic uncertainty, quantifying how far the test point is from the training set, and a noise contribution, which is characterizing fluctuations in the data that the model can't capture. Here's a simple one-dimensional Gaussian process. Here we're modeling the energy of a hydrogen dimer. So what is the energy as a function of the separation of the 2 atoms? And the key point to notice is that as you get closer to a training point, the uncertainties decrease, and as you move away from the training manifold, the uncertainties increase. This property of the uncertainties, which is essentially telling you when you're moving away from the training set of the model, can be exploited to automate the training process. by learning the force field on the fly during molecular dynamics. This diagram here is showing you how this works. So you start with an initial call to DFT on the right side of the loop, and you create an initial training set for the model. If the estimated errors on forces in the simulation are too high, you stay in this right loop, making calls to DFT and updating the training set. At a certain point, the uncertainties fall below a threshold value, and you enter the left side of the loop, updating the positions with the Gaussian process force field and making force predictions much, much faster than with DFT. The drawback of this approach is that it requires you to keep the training set around when you're making predictions. In particular, you have to perform an expensive loop over all of the training points in order to make a prediction. What's needed is some way to map the Gaussian process onto a faster model that allows you to scale up the simulations to tens of thousands of atoms over nanosecond timescales. This brings us to our unified approach to combining the principled uncertainties of kernel-based methods with the speed of linear models. This approach works for a specific class of kernels called dot product kernels, where you take the dot product of two vectors, d1 and d2, and raise it to some power. And here we're raising it to a power of 2. You can rewrite this expression for the local energy as being quadratic in the descriptor vector. So in the bottom right here, the key thing to notice is that this matrix beta is independent of the training set size. In other words, you can take a Gaussian process-based force field that was built on this dot product kernel and map it onto a much faster linear model that's linear in the square of the descriptor. So I'd like to show you how this works in a particular material that we've been applying it to, nitinol, which is nickel titanium, half nickel, half titanium. It exhibits an interesting property called the shape memory effect. Briefly how that works, if you take, say, a paper clip of nitinol and you deform it, so you stretch it out and form some arbitrary shape, the amazing thing about shape memory materials like nitinol is that if you heat it up, it will actually recover its original shape. What's going on at the atomistic scale is a phase transition between a high temperature austenite phase and a low temperature martensite phase, which has a monoclinic distortion of about 98 degrees. Now let's try to learn the phases of nitinol on the fly. So in this plot, I'm showing you the cohesive energy as a function of time for 3 different on-the-fly simulations that we did, starting from 3 different phases of nickel titanium. The blue line is initially in the low temperature martensite phase, which is stable. You can see that the cohesive energy is roughly constant as a function of time. For the other 2 phases that we tried, the green line and the orange line, they were initially unstable, and you can actually see them transform into the stable martensite phase, as you can see in the video graphic here, which shows you the B2 phase transforming into martensite. The black X's in this plot are calls to DFT. You can see initially there's, in each case, a cluster of calls as we get a good model. Since we're starting from scratch, nothing is initially included in the training set. As the simulation unfolds, we need less and less data until eventually it essentially runs on its own without making calls to DFT. Because we're able to take our final trained model and map it onto an equivalent linear model, we're able to scale up our simulations to thousands of atoms. In this case, I'm showing you a simulation of nitinol consisting of 5,600 atoms, and we're able to simulate this with an efficiency of about 1.5 nanoseconds per day on 64 cores. What you're seeing here is the transformation between the high temperature austenite phase and the low temperature martensite phase. In this figure, we compare our model against experiment by performing a cooling heating simulation of nitinol. We start at 500 Kelvin on the lower segment and cool the system, moving to the left, until at 290 Kelvin, we see an abrupt increase in the atomic volume as we transform to the martensite phase. We continue to cool to 100 Kelvin, and then we heat it up, moving to the right along the top segment in the figure until we reach 780 Kelvin, at which point we transform to austenite. You can see the square and triangle are the experimentally measured atomic volumes, and they're in excellent agreement with our model predictions. The code that we use to train our models is available on GitHub. It's open source. We also have some documentation if you're interested in using it. And that brings us to the conclusion. I'd like to thank you for your attention and thank my collaborators. And if you're interested in other applications of this on-the-fly learning technique, which we're calling FLAIR, please check out these other talks at MRS. Thank you, and have a great day.